bring us the methods for new modeling and understanding of also of the material nature. So I will talk today about the chains, about tetrahedral chains which appear in packing problems. But let's first consider shortly packing. If you have equal spheres, then you can pack them on many ways to fill up the space better or worse. I mean, there's a few packing. So this one is a very good packing. You see, this one is less good packing, but it's also good. And this one is not so good, you see. So then there are a few packings. So if you pack, if you have a configuration, say here is 4 spheres, this is common. You see, the bullets of cannons sometimes in ancient, the people were put in like that, and this was a very tight position, yeah, because that one attached 3 points, which is very stable, and of course, as far as those are touching, then the third is very stable. And of course, you can add the spheres, extra sphere here, extra here, and so on and so on. You can add these spheres and build a kind of structure like this one. You can add, if you add 12 such spheres, then you get something what is icosahedron. What is icosahedron, but it's 12 spheres. And there was a very classical problem with packing spheres. And even with Gregory and Newton, they were argued about the problem of kissing spheres. If you have a sphere, so how many spheres can kiss this sphere? Be touched. And then Newton told 12, Gregory 13, but of course Newton was right as usual and was really 12, but with some distortions. So let's go on. So you see, if you pack in spherical molecules or spheres, then finally you got a big holes between the spheres. And then, of course, it's not sphere yet possible to put there, but of course, is some structure which is not regular. You see, not regular. How it is. And so spherical molecules, they are packed to some extent like that. And you can also pack spheres or spherical molecules in some linear way. So then here, for example, is the picture how it is. So if you forget about the structure of the sphere, but you consider only the center of the sphere, centers, then 4 spheres, you see, give the tetrahedron. It's a tetrahedron. Maybe it's better to see this tetrahedron here. Oh, this is this tetrahedron. This is that sphere. That one is this one. That one is this one, and that is that. And these 4 spheres is tight packed. And then next sphere, you see, your next sphere you add here. So this one you add, you see? And then you have this tetrahedron. Yes, and so on and so on. You add only 1 sphere. So for example, I show you on the toy. You see, if you have 1 tetrahedron, yeah, so then you put sphere here, then you have next tetrahedron. And then next tetrahedron, you can put to any side. You have 3 possibilities. You choose one. It doesn't matter which one for a moment. And then you have 3. Then you might again have one of the three, of the last one. This way we build chain. And then you put this like that. Now like that. Oh. And so on and so on and so on. And then you get very interesting chain structure. And I think that nobody was considered this the structure of this type of chains made of equal spheres. But now I show you how it is. And Coxeter discovered. I mean, he wrote about the kind of linear tetrahedral structures, and that's it. But he didn't mention about the kind of a general structure of such tetrahedral chains. And you see, so we replace that spheres, molecules, by their centers. So we get these vertices. Yeah, you understand. And then I show the a program, how it is built up. I mean, if we build such stuff, then see, then you attach. If you attach one sphere, then the same like you attach one tetrahedron. So that each tetrahedron is a reflection of the previous one, because this is just spheres of equal size. So then you see this is like that, and of course there is impossible to go further because that's not possible. Then of course you have to stop or self-intersect. So let's show you some other. So then maybe the visibility, you see some longer one has strange structures, might have. This one is a ring structure. I choose the ring structures and I show you the programs which are doing such things. And this is quite not easy to find the shape. But of course, theoretically is another story how to describe it. And then the second part of my lecture will be on mathematics. I mean, formulas and so on, how to understand this structure. It's still, I want to show you the moves. Yeah, so see. So then each tetrahedron is reflected. And still this is, but never touched, never. Well, which one was that? I mean, this one now. Still, this. I like very much ring structures, but of course not only ring structures are here. Maybe I prepared only ring structures in this moment. Okay. Then you see what we've got. We've got some. If we do such things, add this tetrahedron to each other, reflect. So previous tetrahedron we reflect and we get new one. So we get, for example, such structures, but they never are closed. I mean, there is a very small gap. Always, they never close. They never close. And there's a proof of that appeared some time ago. Some proof. There are a few proofs now, some other proofs. And now, what is this? If you look on this, on that, on this chain, you might see there are 3 units, 3 basic particles of this chain. You see, I have now one kind of complex of 3 tetrahedrons. So this element is always in such tetrahedral chain. And then these are three tetrahedrons. And always they're isomorphic, I mean, isometric with other. But if I add fourth one, there are 3 possibilities. This possibility, then this possibility, and this possibility. There's, yeah, which we call it, you see, down, flat, and up. So you see, these 3 are the same. These 3 are the same. They are always isometric. But this red one is other side. You saw green one is our side, but yellow one is just giving flat structure. Because if you join take a vectors joining the centers, then you get 3 vectors, and these 3 vectors here stay on the plane. So the determinant formed by these vectors is 0. In here, if you form the determinant is plus, is not 0, and but this determinant is minus, also not 0. So this is distinguishment of these 3 roots of the chain. Very beautiful structure, let's say, and of course these are really roots. I mean, there are different elements which form all very complicated chains. And then how to describe the other chains. So let me show it this also in such way that you may see it better. You see, this is exactly seen, I mean, in different way. Yeah. Oh, this is F. But I should perhaps to make it like that. You see, they are different. But of course, you have to look a bit. This is, you see, this looks like similar, but they're not the same. You see, this is this 3. You can see that these are different lines here. Yeah, there's a difference. Yeah, this difference is that one tetrahedron is other side, one side, another side, and this is flat. You see, because you have always three possibilities. 3 sides, one, other side, and this side. Yeah, but these 3 possibilities give, in fact, 3 units after these 3 initial tetrahedrons giving always isometric group. And then, here you add extra. Even if you have this F, you have FF. This one, FF. You have these 3, and then you got this one, this F, and then you start from the second one, and you get another F. But if you have to understand it. If you don't, because this is the simple construction. So if you have a question, then please, because people somewhere they might not give the question, because if they are here, that's much easier. I would show them using this guy. Okay, so then, you see, now there is a structure UDFDU. And then it's easy to figure out that this is so, but this looks like strange. But this is the form. And then this form is written as the word. Udvdu, 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 udvdu. You see? And whatever you say, it has a shape. So you can, the words, they have shape. And then, yeah. For example, such word. You see, such word is just this ring, part of the ring, because it's never ring, it's never closed. I show you that, and we ask people to give us the word from the internet who are looking, and then we construct then everybody can construct its own chain. But that's a moment. You see, these are some other constructions. And I mean, geometry of that is not so trivial. And why this is not so trivial, I will explain. You know, these are examples. These are also transparent. You see transparent things. Yeah, and the random chains, the dynamics of growth. So the dynamics of growth is looking like that. So, you know, already I showed this. That might be very different structures. It depends on the word you say. Okay, so you can everybody from the who is attending this course now will tell us the word. Yeah, they can send us the words, and I will show them the program and how to prepare the. Yeah. Even now, if you like. You see dual chains. Okay, if people want, then maybe even now. Okay, so then let's. Mm-hmm. And there are also dual chains. You see, dual chains. Dual chain is there's a tetrahedron. Dual is just joining the centers of the sides of the tetrahedron. And dual chains, you see, they attached by vertices. So that's also nice, but it's a dual. So then the geometry of this is in principle the same, but of course looking like different. But some toy in the but you know, and also the structure is in the word. Yeah. And then what we call this, you see this very, you see there's this gap. We call it Pythagoras gap, because if there is no this gap, there's no life in the earth. So people say that Euclidean, if the space is curved, then there is no this gap. So maybe good that we have a Euclidean space with zero curvature of this, because otherwise we might don't survive. I mean, this gap is giving us the variety of forms, infinite variety of forms in Euclidean space. Life is local in some sense. And as you see, because we are not so big. Of course, the biggest animal, maybe elephant, I don't know what, no, biggest of them, maybe are bigger, but they are still local. So this is the distance. It depends on the number of the length of the chain, and they're smaller, but they still exist. There are also, you see, the closed. Oh, you see, you can stop there because you cannot go further because then this is closed. Okay, and then we can also consider the this is the protein waving problem. Protein waving problem answer question how the proteins are waving. The structure, geometric structure of proteins, the ternary structure is very important. Properties of these geometric properties is just the Drax properties. So there's such structures. They change other structures. I mean, geometrical structures. So geometry, in some way, the configuration of the particles of the proteins in the protein are very important. So then here are just optimal forms of some chains. In only six chains which are built on one vertex. On one vertex, so all these tetrahedrons have common one vertex, and there are only 6 such possibilities, and they have such graphs. the graphs are not isomorphic. No. So there are 6 graphs. These 6 graphs built are also roots on ternary structure. So that's, you know, the building of the world is just many levels of the structure. It's many levels. People sometimes don't recognize these many levels and live in one level, and they think that they know everything. Oh no, it's very difficult to know everything because there is infinitely levels. Okay, so you see then even such complicated, no, they're not complicated. This is just maximal. You see this, this optimal objects right here. From that, the higher organized chain is built. So then also this is possible, and it's important to understand because it's just a waved protein like that. Yeah, and then if you consider this, you see, if you consider, I can use the blackboard. Yeah. If you have this tetrahedron, and then you see this is the center of this tetrahedron. Then if you add tetrahedron next tetrahedron here, then you have next center of it, and you join this center. Then you have third tetrahedron, you have center here, and you have also third here, and then one which is here. So this is the tetrahedron, and then another one. And then we get a tree. You see, at each point we have 3 isogonal. So then this is isogonal, everywhere isogonal, and each we have, and that's this these intervals are equal, and so on and so on. And this tree is called the tree of life, because in fact each while of the next moment is the reflection of the previous while, and this reflection is isogonal. Then we get such I call it tree life, tree of life, because this is, you see, if there is more of these reflections, then dense and dense and dense, and what happens is extremely interesting. You see the structures of the kind of dodecahedrons, which are approximate dodecahedrons. It's not enclosed. It's never closed. It's just dense structure. Okay, and then what was used this one? That was, we used some project to nanotechnology. Nanotechnology is a situation like that nanoparticles, you cannot do much with nanoparticles. You have to construct some conditions that they do something, these particles. They go together, they move somewhere, they attach each other and something like that. And then there was a project to build a kind of nano transformer of drug. In our body, if you have injection of the somewhere, then the drug is going everywhere in your, and then sometimes it's coming to the sick place. But then there's a question how to build the transporter, how to transport the drug to the sick place, just there, to give the very big density of drug in the sick place. And then this is just the way. You see, it was kind of producing the some plant which takes a spray, some you see droplets, which in this in this plant, they became a kind of nanoparticles, like of blood particles. But of course, they are not blood. And these particles is a technology is here. You remember, this is invisible problem. This is invisible. It's so small that eyes are not visible. But of course, it's possible to see it if you have a microscope. Then, of course, it's possible. Special microscope, then you can. And then you see that there are few particles, and in the drying process, this small particles, you saw minus is written. And even smaller silica particles and negative zeta potential and PSL particles, and they, after drying process, these PSL particles escape, and these small silica particles form the shell with holes. You see, this is the hole. These holes is after escaping these particles. So these are holes. So this is a kind of ball with holes, but nano ball, and that's very hard. It's very hard, made of silica. So you see, and then why this is so important? Because, and then you see, this is nano. The model is so because we can build such things, and also we can build. This is what we really need: these porous particles with holes, because then we take the drag, we put drag to them inside, to these holes inside, and then put to the body, and magnetically, for example, go with this to the seat place. And then density of drag is huge. For land, it's very useful. It's already in chemist shops, I think, but I'm not sure in China. But this is very strong because the drag is going just to the place which is sick, and no some other way. And then there is problem still in the blood, because you know, if drug is used in the practice, then it should not be killing body. You know, the producers should prove that it is safe. So of course, for lung, it is possible to prove, because it's possible to withdraw these particles back. I mean, the silica material back from lung, but from blood, not yet. So only experiments, not yet used in practice. Okay, so you see there are these holes here, and then this is mathematics. How does mathematics help here? Very simple. I mean, very simple. Not cohomologies of the space help. No, not the global. That's global things. There was a question: how many networks, isogonal networks on the sphere? It appears that this is 10 such isogonal networks. And then the density of these particles, the bigger particles, is not so many. It should be among them, between say 2 or 20 or something like that. And then only after this knowledge, theorem about the classification of isogonal networks on the sphere, you are able to get these structures. So you see, mathematics is important. Saying something for practice, for experiments, you know. If you don't know, then you can, of course. If you are blind, sometimes you are lucky to get something. If you are blind, but if you see, you get it better, quicker. Okay, so you see, this is just the big zoom of these particles. These are real. Also in DNA structure, this is used, because we have this nucleotides, adenine, guanine, thymine, cytosine, and then even if you take 3 of them, and D, U, and F, then we have just particles. We have the DNA structures. Of course, not all the maybe amino nucleotides, but that's we have. No. And there are here geometric coding of DNA sequences of the, you see, of the left one is just using the UDF codes. Yeah. And now maybe we can do this exercise. If someone wants to, then let's people showed us. Maybe I open the program. The program. This is the Maple program. Oh, you see, and then. And now let's, you see, that's a program, and then it's written here the word. Word is here, you see? Word, oh, this is the word. UUFGG, you see? This is the word. This is the period. 7 times this period. But if I take one, no period. So let's, everybody who is watching this move, say some word in using U, F, and D. Then I execute that, and I get, yeah, this is program working, and I get, and I got what I got, oh, just such thing, but very short. This is very short because the word is very short, you see? The word is very short. Then I got something like that. Word is here, UUFDD. Let's people send us the words, and then you tell me, and I write, and then we get it. You first U, F, and what else? So longer, because this is very small. F, then U, U, yeah. No, it's still short. You can put very long, but it takes time to calculate. But then it's, say until say 50 is no problem, because you see the period is 1. If I take a period, then this is multiplied. But then okay, so you told something like that. So you told something like that. So then we calculate and we look what's the shape of that. Your word. Maybe you got a very beautiful shape, or maybe very complicated. You see, and then look what's going on. So you got something like that, you see, and then it's self-intersecting. It's self-intersecting. So this is such what you told. Like, your what? Not good thing. Not good thing. Yeah, but yes, this is sometimes there are rules when it's self-intersecting or not. But yeah, so no, easy. Now you want. You might want to have this periodical. You might get so if NC I put not 1 but some other number, then it will be period. No, what your word? Maybe laugh or something, yeah. But using UDF. Okay. UD FD and yeah. How what? D Okay. No more. You know, if you take more than 2f, then it's self-intersecting because this is just the DD. Okay, let's check. Calculating, you see, but let's calculate. Oh, you see, that's self-intersecting, I think. You see, it's not so easy to find a not intersecting, but that's possible. Oh, it's your word, you see. Oh, that's not self-intersecting. It's very nice, you see. Yes, it's not self-in. I something strange here. You see this one here. Yeah, this is touching that, but perhaps not self-intersecting. So you see, this is your word, you told. So maybe people tell us some words which, if they are there, they don't get. No, use the D and F, but not repeat F more than twice. But of course, if they repeat, then it's okay. But it will be self-intersection. No. If you repeat F twice, then certainly self-intersect for sure. Yeah. But twice, no. But of course, it's not theorem which says when it self-intersects. We calculated number of non-self-intersecting chains until not so long, because it's very difficult program for that. So that's and this is for PhD of my student who done this program. It was a very fancy program. So no, people don't want. There is some. Nobody wants. Nobody wants to have to say some form. You can tell in Chinese. Nobody. Oh, but they shouldn't. Okay. Of course, you see, if I take something like that and put here not one, but some period, say 10. If you have 10 and this is 40, say I have 40 word, 40 characters. Then UD, you see, then will be something like that. It's very complicated. I mean, not that complicated, but self-intersect. You see, it's self-intersecting. Kind of oh, such object. Interesting. And it's never closed. So then, like cylinder, like drum. So people, musicians can use it as a drum. But it's not so beautiful. Beautiful will be if you go out from that. So then we put F inside. So then we will see what we have. But you see the period is 10. 10 times I repeat this. This is maple. So people here, I mean, these college students are so excellent that they know how to do this type, I think, programs. You have the programs, I think, in Yahoo Center. Oh, this is also complicated. So then, Yeah. Yeah. So then we can check. We can check the case. You see D, U, or like that, and then like that, and then we'll see now. It's calculations. If it is longer, then takes longer time because it's calculating and also graphics. Or you see, now we don't get a ring. We get something like that. Some structure, helical structure. You see, helical structure. Oh. No, but it's small, but that's the moment I make it bigger. Oh. Oh, you see, something like that. This is just the mm, mm. The name of this is DDFUUD, but nine times. Yeah. Oh, food. Okay, food. We take food. Food. Okay. We see what is this. Food. FUUD. Well, maybe that's not. Well, that's not. It's calculating. Again, always appears such thing information. Oh, again, the linear structure, kind of linear, I mean helical structure. You see? Some not big difference, but some helical. And well, that's because yeah. So that break now. Okay. They are Pythagorean, but let's be Platonic if someone because Plato was extremely excited of these bodies, but he didn't prove it. That proved some other mathematician, Tetateus, proved that there are 5 such structures. You see, this is then Plato was so excited that thought that this all of you observe the world is just these figures. So the first one, tetrahedron, was fire. Then cube was earth. Dodecahedron was the icosahedron was the water, and octahedron was wind. And then the left was dodecahedron. Dodecahedron was left, and so were the 4 roots that time, and the 5th was not. So then he decided that the dodecahedron, the last one, this is so beautiful that this is the cosmos. All the all the world is just the dodecahedron. And then later, during the Kepler and Poinsot time, appeared that there are 4 more figures which are not convex, but also regular figures. So you see, this 4 here, no, that's here, but this 4, there are also regular, but they have the same faces, but they are not convex. So this is the full kind of set of beautiful regular bodies. This is 9 of these bodies, not 5. If someone likes convexity, then 5. If non-convexity, 2 also, then 9. So the structure of the nature is just modeled by this mathematics. So mathematics is just everywhere. Material world is mathematics. So and then I repeat what about this packing, the square packing, face-centered cubic packing, and this were Barrow-Boyce packing, which I showed before, rhombic dodecahedron packing, And then these packings were, of course, discussed long time. And then this problem of Newton and Gregory in 17th century, the kissing number, Newton was right, as it was proved only in 1953. So a long time it was left as a hypothesis. And then why this is so? Why this these chains, tetrahedral chains, are not closed? Because if you consider icosahedron, then in icosahedron, the distance of the vertices A, you see, is longer of 5% of the distance of the vertex from the center. Because of that, it's never possible to close the tetrahedral chain. Yeah, because of this distance difference. If that B is equal A, that will be closed. I mean, no word, no life, perhaps. So this is the reason. And then this one, what I showed you, these tetrahedral chains. Again, I repeat, it was our Polish Steinhaus who solved this problem, but didn't form this way, in some different way, and considered it. And also Mason in 72 proved that they are not closed, not close. And then the tetrahedral chains they have helical structure like that. Tetra like ring structures. Also, almost closed tetrahedral chains. Almost, you see, you never don't know. You even don't know where it is closed. It's not closed, but the distance is so small that we don't see it by eyes. And then dual tetrahedral chains. You see this small gap here. This very small thing. This is just the sense of our world. Because if this might be, these points might coalesce here, then nothing possible. Now we have infinity varieties of forms, and then we can choose, and the body can find its form. And how to describe this? You might see this a bit difficult, but that's not big. This is very trivial. You can forget this. People who are watching that and they have problem with this sign, with this sign, then forget it. This is the usual. You can consider it as a usual multiplication. But this is multiplication of vectors, yeah, vector spaces or something. That's called tensor multiplication, tensorial multiplication. So then, but this is really not, and you can also don't take into account. So what is tetrahedron? Tetrahedron has 4 vertices, you see? And these are faces. So opposite to this vertex. And then there are pairs, four vertex and the face opposite. So like here. So this is the face, this one is the face, and this is the vertex. So P1 and this S1, P2, S2, and so on, and the 4 of such. So this is very simple. So this is a regular tetrahedron. Regular means that all these objects, I mean faces and sides and they are the same. So that there's differences. This lengths of this side of this intervals are the same. And then regular tetrahedron is an element of such tensor product. That's why this is tensor product is another story. This is quite simple. So V is a configurational affine space. This affine space in which we are alive. So this is 3-dimensional space. This one, distance, I mean height, left, right, and so on. And we have barycentric coordinates. Barycentric coordinates, people, I think, study in high school, maybe, no? If not, then there are, say, coordinates, some numbers you see of 4-dimensional space. Sum of them is equal 1. So this is the coordinates of tree space. You can always construct such coordinates. And so this is canonical hyperplane and barycentric coordinates. And then if you have the tetrahedron there, T belonging to this space there, then this is nothing else but just the tensor product of these vertices and just some elements of the barycentric coordinates. And the tetrahedron is a barycentric coordinate map, T, acting on alphas, which are Euclidean numbers, and gives just nothing else but this number. This number is a point of the tetrahedron. So coordinates of the point inside. And if you go through alpha I on the hypersurface H with alpha I positive, then you get this body. Point by point, you get this body. So this image T of this piece of hypersurface gives you physically this body. I mean, physically, geometrically. Each point, if you take the point here, then you get all points of this tetrahedron. And then we have, if you have a mapping of the space, a fine mapping, so F leads to a linear mapping of this barycentric coordinates, and preserving the hyperplane. And then this is some mathematics, very elementary mathematics, but I think that college students might know. And then if we take these superpositions of these objects, then we have equality. And why this is so important? Because we need to construct the reflection. We reflect one tetrahedron, and we get another tetrahedron. And then this is just in barycentric coordinates. This affine transformation is defined there. And then, of course, we have this something which is relatively trivial for description. And then, how we generate the tetrahedral chain? We take the, center of phase, SI, small si. What is this? This is just 1/3. That's the center of this triangle, equilateral triangle, center of this equilateral triangle, which is SI. And we have 4 orthogonal reflections, because four sides and at which we have reflection. If we reflect we have tetrahedron. And then we reflect this vertex in this side. So this one is Si, and this is S small I. Then we reflect, and we get this one. This one. This is reflection of that in this side. This is this side is mirror. So this one is reflected. Yeah. And of course, we do this 4 times with each side. So then there's 4 orthogonal reflections by in mirrors, which are the sides, are written. This is a formula. This is the usual school formula for reflection. For reflection in the plane. Yeah? And here in the plane pass through the side. So this is reflection. You see reflection in one side of this vertex. So this giving to another vertex, another tetrahedron, and so on and so on. So we construct this this chain by reflecting the previous chain in some phase. This is just technical assumption to give the to make a program for calculations. You have to always, if you want to visualize something or really do this, you have to make it practically some concrete things here that you have to make the coordinates and so on, reflections. Then we have 4 orthogonal reflections in these mirrors. So the face of the side of the tetrahedron is a mirror. We have 4 mirrors. So each side is a mirror. And then these are just reflections. So if you take the point in the space, or the space, then your reflection is like that. And you see that if you put here other vertices, then they are constant, the same. Only one is not for I not equal j. See? If I is equal j, then this is 0, because this is 1 if I is equal j. You understand? Yeah. So then, if I is equal j, then this is just 1, and then you get new coordinates. New coordinate, just new vertex in the space. If you consider here, for example, j equal not equal I, then you get j, because this is 0, and then Ri on Pj is equal Pj. For 3 vertices, they are the same, but this one not. This one gives new one. So maybe, yeah, if you know, these are exercises, if people are coming and we can calculate on the blackboard, this is easy, but that's okay. Then if you consider such reflections, then you get just tetrahedral chain. And tetrahedral chain, you see, if you start with one, with that one, you start with that one. You start with one tetrahedron. Then you reflect it in one side. Then you get another one. You see, you get another one. You reflected this one, you get this one. So you have T1 here, I1, reflected in I1. And so then this and this reflection, so this one and this, a pair. Then it's a 3 of them. This, and that. So then it's written this tetrahedral chain as a you see series of reflections in this tetrahedrons, subsequent tetrahedrons. So then end point is, you see, you have this initial tetrahedron and reflections. But of course, what is here important, that your choice, which reflection, you always have choice among 3. So this is why this is the branching phenomena. And this is just constructed of reflections. And how to describe it? Oh, that's not so difficult. If you have this P1, P2, P3, P4, then they are transformed by these matrices. So there are 4 by 4 matrices which transform the vertices. And there are 4 such matrices, but of course, only 3 are acting in one step of the process. So then here is example. You see, this is just, you take this matrix. This is what is written here in different way. You have this matrix, and your reflection is the actant of this 4 by 4 matrix on these 4 vectors. That I think the college students may know. And then you get new vertices, and you see the P2 here is going into P2 because this is 1, and the P3 into P3, P4 into P4, but P1 is going into 2 over 3 P2 plus 2 over 3 P3 plus 2 over 3 P4 minus P1, and this is new P11 because P1 here is reflected. This is really reflected. This one, they stop. They are, so that means these are just fixed, but this one is reflected. This is P1, P2, P3, P4. And P1 is reflected, and we get new coordinates. Yeah. So then you see the coding in triplets of consecutive steps. So consecutive steps is just the case, and the UDF is very naturally defined. This is just the determinant of this of these differences. You know, TR plus R plus 3, TR plus is just positive, negative, or 0. These are, you see, T and 3 reflections. Together, 4 tetrahedrons form the unit, UDF. Well, that's. Or you see, this is just the case. This is this vector, that, and that. So in 4, this form. And these 3 vectors, determinant of these 3 vectors in R3 might be 0, 0, this is F, plus this is U, and minus this is D. And that's, I repeat what I showed before. This is exactly that. And then again, mathematics. And then, no, these are now the combinatorial codes of this chain. No, well, now we have triplets of numbers, you see, between 4 and 1, because there is only 4 vertices. So we have numbers, not big numbers we have. We have numbers from 1 to 4. You see, but we have triplets of numbers, and they never repeat. But they, I mean, if it's I, and on J might not be I, because then this is reflection. Reflection is involution. If you make it twice, this is identity. So you cannot, so this is why K is not equal J, and I is not equal J, A is not equal J. So then something like some word, we just write combinatorially. So combinatorics here is very interesting because we can describe these vertices by numbers in many ways. So if we put 1 to the 1 vertex, and second, third, and fourth, then someone says, why not 2 put here, but 1? Okay, you can put here 2, and the other numbers. So we try to find, I mean, we find the description which does not depend on this, which number you prescribe to vertices. Whatever you prescribe, then always gives by these rules the same result. So now there is some prescription. So if you have, you see, 3, 4, 2 for this, what is this? This is just saying about the reflections. You see this? This is the numbers. These numbers move says in which side this tetrahedron is reflected. You see, they never repeat. I mean, it's not 1, 1 or 4, 4, never. Yeah. So then this description is like that. You see, this is just the description of this site. Yeah. Oh, and then this is also the word which gives such shape. If someone writes this shape, this word, and gets such shape. This is the same shape seen from up. And this is just the classification of admissible triplets. So triplets, admissible triplets, give the cases U, D, and F. So U is described, you see, by 12, by 1, 2, 3, 4, 5, 6, 7, 8, 9, by 12 triplets. Each one by 12 triplets. So if you choose one of these triplets, this is F. And of course, after reflection, you change, as you know, if you reflect space, you change orientation. Something what was left, now after reflection is right. So this is also important, but that's some technique. And then you have this representation by these numbers. I think that students like numbers. So that's numbers, very easy. The paper is published, you can always check exactly what's going on. And from these triplets replace these characters U, D, and F. And how they join, then I already showed, but this is so. And then, for example, if you want to have such a chain like U, then this is the all they 1, 2, 3, 4, 5, 6, 12 such descriptions. All describe U chain. You understand? Yeah. And DD chains describe all these. Yeah. You see, this is like that. This one is forgotten here. This two one, because this is always like that. Previous tetrahedron is forgotten, and the last two are taken into account. So there are last two, and then last two and extra new one, which appear in the chain, and so on. This one here, and this is forgotten, and extra new one, 3, and so on, and then and so on and so on. But of course, someone says this is too many. Yeah, we can now make some order and show the classes, equivalency classes. We define these words. So, but listen, you understand what I mean here? So this is 3 reflections. So you have, say, 3 tetrahedrons, and then you have this fourth, so first one and 3, so that together 4, and then you forget this one, the first one, and you have only 3. So you have to add 5th one. The 5th one has by reflection here to this 2, 4. Reflection in vertex 4. But you have to forget, because if you have the chain, then of course maybe this is easier to show on that. I can understand if this is of course simple, but after someone already experienced that. Then if you have such element of the chain, such element, then you add here new element. You see, to get this, you have 3 reflections: reflections in this face, reflections in that face, and reflection in that face. Now you add some here, then forget this one, and then adding this, you reflect in some. You understand? Then again, forgetting this, and reflecting the last one. And this is choice. Yes, you walk in, you forget the last one. And these are just reflection. This is reflection, these 2, as the same, because there are two reflections are the same, but for third reflection reflects fourth, in fourth. And then again, this is left, and this is forgotten because this is that first one, and so on, and you have this chain. Yeah. Okay. Oh, there is a combinatorial structure of this is just the very interesting thing. So then there is some because I think that my time is going over. So some examples of that and so on. And this tetrahedral group is just very important. Here is everything has the structure. And this is the proper tetrahedral chains, which are not self-intersecting, are calculated until number 13, you see? Length 13, so not so long. So this one, we know we had 41,000 of chains like that. Branching order, you know, order is between 0 and 3. Vortex order is calculated. Clustering function, which is minimalized here. And then tetrahelix, which appeared in literature before, is something very regular like that. Zero branching order type, and so on. These are the proper chains starting on common vertex chains. So this is that. And this icocluster, the common vertex, this one, these are the words very defined. And this, yeah, then earlier. So this is the smallest unit for B equal 1. So B, this is the bifurcation point, bifurcation number is 1. And then there are some clustering, folding. You see, this is looking like that. Big periodic, mixed clustering, folding. And this is published in the paper by me and my PhD student, combinatorial representation of tetrahedral chains, communication and information. You can find this easy. And that's it. This is also the repetition of that what was used for. This is just that on this very concrete achievement of nanomedicine. This is achievement of nanomedicine. Nanomedicine is very important, you know, because we can wonder on our body using nano size. So thank you very much for all who participated. Next week will be easier without even easier. So let's say. Thank you. Thank you very much. Oh no. Do you switch off? Not yet. Then